Hello all, welcome to the channel. So I'm starting with refrigerator today. So this is under again thermodynamics. So this is my sixth lecture on thermodynamics. So the refrigerator, as you all know, that is a device for cooling things. That as simple as that. But now, how the process works here? What are the things it requires to work on? So we need three again. One is zinc, another is working substance, another is source. But in this case, all is same, but in this case, the working substance would absorb a certain quantity of heat from Q2, as you can see. It is absorbing heat from sink that is at lower temperature T2, and it rejects a amount of heat that is Q1 to the source which is at higher temperature. So it is done with the help of external agency. Now in this case you can see the external agency is electric motor as shown in the figure. The arrow, as you can see, is towards the working substance. So if it is towards the working substance, that means it is doing work on the working substance to work on. Now, therefore, the working substance would work only on the basis of electric motor in this case. It is not providing some work. In this case, we are actually providing external agency to the refrigerator, that is electric motor. And the process is opposite, as you can see. It is absorbing heat now from the sink, not from the source but from the sink, which is at lower temperature as compared to the source. The source is at higher temperature, and the working substance is giving heat off to the source, that is Q1. Now this is again a reversible process, as the initial state is again reached. So in this case again your internal energy will be zero, as in the case of heat engine. But in this case the work done will be dq will be qt q2 minus q1. And what will be the work done? It will be negative because we are providing it with work. So the del W will be minus W. Now, according to the first law, so first law is del Q equal del U plus del W. So del Q in this case is Q2 minus Q1, del U is 0, del W is minus W. So in this case it will be W equal, rearranging these, so it will be W equal Q1 minus Q2. So the work done is the difference between Q1 and Q2. Now, as in the case of heat engine, derivate we did derivation of thermal efficiency. In this we would be finding the coefficient of performance, like what will be the performance of the refrigerator at different temperature. So the coefficient of performance. So it is actually defined as the ratio of quantity heat removed per cycle from the content of refrigerator. So that will be Q2 over the energy spent per cycle to remove this heat. So it is work done. Now the work done can be replaced with the first equation, that is Q1 minus Q2. So Q2 over Q1 minus Q2. Now I would be dividing the numerator and denominator with Q1 to make it a perfect equation. So Q2 over Q1, Q1 over Q1 minus Q2 over Q1. So Q2 over Q1 over 1 minus Q2 over Q1. So this is the equation, but if you want to write in terms of temperature, then from the Carnot cycle, it states that Q2 over Q1 is equal to T2 over T1. That means I will be replacing all Q2 over Q1 with T2 over T1. So T2 over T1, 1 minus T2 over T1. Now taking LCM, it will be T2 over T1 over T1 minus T2 over T1. So T1 and T1 gets cancelled. So the equation in terms of T temperature, it will be T2 over T1 minus T2. So this is beta, that is coefficient of performance. And if you need to write beta and neta terms, so it will be, so if neta is efficiency of Carnot cycle, so the formula for it is 1 minus T2 over T1 for Carnot cycle, mind you. If not Carnot cycle, then you can use this. If it is Carnot cycle, then you can use this formula to put in. So from this it will be, I will be finding T2 over T1. So it will be 1 minus neta. So beta can be, using this equation, it will be 1 minus neta over neta. So this is the relation between beta and neta. So thank you for watching this video. Have a great day.